Hello everyone, we are Tech Decks. Today, let us have a look on our space weather monitoring system, a satellite-based monitoring system for predicting space weather phenomena. Our problem statement for TACMagran is to develop a satellite-based monitoring system for tracking solar storms and predicting space weather phenomena that integrates data from solar observatories, magnetometers, space weather satellites to forecast geomagnetic disturbances, auroral activities, radio blackouts, enabling mitigation methods to protect satellite assets, power grids, and GPS navigation system from space weather related disruptions. Let's understand the problem statement. Okay, what is solar storm? Solar storm occurs when the sun emits huge bursts of energy in the form of solar flares and coronal mass ejection. These phenomena send a stream of electric charges and magnetic field towards Earth at a speed of about 3 million miles per hour. How does the solar storm that occurs in space affects us humans on Earth? Effects on communication. During geomagnetic storms, which are results of solar storm, some radio frequencies are observed and others are affected, leading to rapidly fluctuating signals and an unexpected propagation path, results in public and amateur radio signals being frequently disrupted. Effects on power grids. When a solar storm induces currents on Earth's magnetosphere, these can overrun the power grids, potentially exceeding 100 amperes. These surges can damage the delicate components of transformers and cables. This is similar to an overloaded electrical outlet. Effects on GPS system. During these space weather events, disruption in satellite signals passing through the Earth's ionosphere can result in signal degradation and compromise the overall reliability on the GPS technology. For instance, single frequency GPS system can experience errors up to tens of meters during severe space weather events. This is the outlay of how we are going to develop our solution for this solar storm and its effects. Okay, basically we'll be collecting real-time data from space weather satellites, solar observatories, and magnetometers, collecting these data and integrating them, processing data for analysis. We'll be having a trained ML machine learning model for forecasting geomagnetic disturbances, auroral activities, and radio blackouts. Parallelly with this real-time data, we'll be having a visually pleasing dashboard uh, for real-time monitoring and automated alerts for satellite operators, target management, and GPS system and service providers, uh, along with mitigation measures being provided for them. Data collection and integration. We'll be using different APIs for collecting real-time data. Some of the APIs are listed here. HelioWeaver API, Solar Dynamic Observatory STO data from NASA for solar observatory and space weather satellite data, and NCEI API, SuperMag API, CDA Web API, and SpacePy Python library for magnetometers data. Predictive analysis. We'll be using historical data to understand patterns and correlation, identifying relevant features such as solar wind speed, magnetic field intensity, and solar flare magnitude. We'll be developing a machine learning model. We'll be using random forest model because it best suits for weather forecasting. We'll be training them with the historical data of past solar storms and geomagnetic disturbances, and testing the model's performance with a separate data set to ensure accuracy and reliability. This random forest model will be used for forecasting geomagnetic disturbance, auroral activities, and radio blackouts. Real-time monitoring and visualization. We'll be having interactive dashboard, a user-friendly interface displaying real-time data and forecast, accessible to all stakeholders including satellite operators, power grid managers, and GPS service providers. Visualization tools will be using a graph, heat maps, etc. Automated alerting system, sending real-time notifications to stakeholders via email, SMS, and other communication channels. We'll be having customizable threshold for our users, allowing them to set specific threshold for different types of space weather events, ensuring alerts are relevant and actionable for each stakeholder. For example, satellite operators will be warned to adjust satellite orbits or put systems in safe mode. Forward managers get alerts to prepare for potential geomagnetic induced currents and implement load shedding plans. GPS service providers gets notified about potential signal disruptions and suggestions for enhancing error correction. Mitigation measures. This will be based on the historical data. Satellite operators will be getting a recommendation for adjusting satellite orbits and orientation to minimize the exposure to harmful solar radiation. Implementing shielding and safe mode protocols for non-essential systems. Power grid management will be getting strategies for reducing load on vulnerable sections of the power grid during geomagnetic storms. Reconfiguring grid operation to prevent widespread outages and damage. GPS system providers will be getting enhanced algorithms in GPS receiver to maintain accuracy during space weather disturbances, notifying the users about potential navigation inaccuracies, and suggesting alternative routes and timing. Thank you.